Hi, I'm Andrew Ray. I'm an assistant professor in the Division of Aquaculture at Kentucky State University, and I'm here to talk to you today a little bit about water quality, some of the basics of water quality, especially those that I think are most important for high school classrooms and the like. So, first of all, what is water? Well, water is actually pretty important. Every living thing depends on water. In fact, even when you think about recent space explorations, one of the first things that most of those ventures are looking for is water, because if there's signs of water, then there could possibly be life, or at least life as we know it. And so everything on Earth that's alive depends on water, at least at some point in its life cycle. And it's imperative that we maintain good water quality, or that we maintain water that's adequate enough to support life. And especially in aquaculture, we're very interested in doing that because the animals and sometimes the plants that we grow in water are highly dependent on the materials and physical properties of the water, the materials that are in the water and the physical properties of the water. Water is a unique molecule, actually. Everybody knows it. H2O, dihydrogen oxide, but the formation of these water molecules is important because the hydrogen and the oxygen are strongly bonded together. It's very difficult to break those bonds. There's an unusual bend in the geometry where the hydrogens tend to be more towards one side of the molecule, which gives it more of a positive charge, and the oxygen on the other side gives that water molecule a little bit of a negative charge. And so it's actually, it actually has polarity. It actually has a positive end and a negative end. And what that means in a body of water is that there's what we call a dipole moment. And there's these hydrogen bonds that form between water molecules, and they're forming and breaking apart constantly, all the time. And this is what gives water some of its unique properties. Water is often called the universal solvent, and that's again because of its polarity. It can pull apart other polar compounds. It can pull apart things like table salt, as we know, dissolves in water. The way that works is that these polar water molecules are actually pulling the sodium and the chloride apart and dissolving those salts. Another one that's relevant to the Kentucky area, for instance, is carbonate compounds. There's a lot of carbonate in our water because of the dissolving of the limestone in our local geology. And so water is a good dissolver, or a good solvent is what we call it. And so this polarity gives water some interesting properties, such as cohesion, because the water molecules are actually attracted to each other, and that's what forms a water drop. You don't see a molecule of water, you usually see drops of water in small portions. And so there's also adhesion, where water molecules, or water droplets in this case, tend to adhere to other things, in this case blades of grass or needles of a pine tree. And then there's surface tension as well. An interesting trick, if you want to observe surface tension in your classroom, is to take a glass of water and carefully place a paper clip on top of that water and see if it'll stay on top of the surface. If it does, then that's an example of surface tension, which is actually cohesion. It's actually those molecules that are bonded together that's causing that cohesion to occur. Capillary action is like what we see in a lot of plants. You can take a piece of celery and stick it in water with food coloring. Eventually the celery is going to turn the color of that food coloring because of capillary action. The water molecules actually move up the capillaries, or the vessels of the plant, the celery in that case. Where's our water? Well, the entire Earth, we only have about 2.5% of our water is fresh water. And currently this tends to be one of the most, well, the most important type of water for most of our human activities. We use it for a variety of things, from industry to drinking, of course, to agriculture, irrigation. That's a huge consumer of freshwater resources, and the other 97.5% is saltwater, which we don't make as much use of. Of course, we fish and things like that. And so then you can see a further breakdown of where some of the freshwater is on Earth. And so with only that very limited amount of fresh water, it's important that we maintain that. 0.3% is in lakes and rivers, 31% approximately is in groundwater, 69% is tied up in glaciers and permanent snow cover, so that's not even accessible to us out of that small 2.5% of fresh water on Earth. The water cycle, this is an important diagram to study to understand where your water comes from and where it goes. I won't go into a lot of the details of this diagram. I think it's pretty self-explanatory, but it's rather complex, and it's important to understand that water's in a constant cycle. It's constantly in one of these portions of the water cycle. So what is water quality? One good definition is that it's information regarding concentrations of specific chemicals or levels of parameters in water that are important to aquatic and human health, aquatic life and human health. And that's a little bit of I took the EPA's definition and changed that just slightly. And why is it important? Well, like I mentioned, water is essential for life. It completely surrounds aquatic animals, in our case, and it is the world in which they live. And you have to maintain that world, or they won't be able to live, or they may not be able to live as well. Human health, of course, water quality, and the people who manage our water quality play an integral role in our societies in the way of drinking water plants and wastewater treatment plants. Most municipalities get their water from, well, most municipalities in Kentucky get their water from surface water, rivers and large streams, and then they return a lot of that water back to that water body through treatment processes. And so it's very important that we understand the processes involved in treating that water and making sure that it's of good quality. When we talk about water quality in aquaculture, here's a list of most of the things that we find to be important. I won't go through every one of these things, but each has significant effects on the performance of animals, and many of these, if not all of them actually, have interactive effects with one another. So the first one to come to is temperature. Temperature is actually a measure of how fast molecules are moving in a substance, and that is energy essentially. But heat is the measure of the amount of energy you have to put into that substance in order to change the temperature. So heat can be added through, let's say, fire. You heat up the water to increase its temperature. When you're doing that, you're actually putting energy into that substance, into the water, and you're making those molecules in that substance move faster. And so it's important to understand the difference between temperature and heat. Those are actually two different concepts. Fish and invertebrates are cold-blooded animals, we call them, which means they're ectothermic. Their body temperature is determined by the environment in which they live. They don't have the means to control their own body temperature like we do, and like most terrestrial, well, mammals and birds and the like. Increasing temperature generally increases the metabolic rate of aquatic animals. And so more temperature means higher metabolic rate. That's actually, those two are directly related. When it comes to aquaculture and water quality, there's a lot of different ways of heating water, that is, adding that energy to water. This is an example of some greenhouses actually that I used to work at, where we had about 75 cubic meters of water in each of these raceways that were inside each of 6 greenhouses. Anyway, the picture on the lower portion of the slide is a couple of natural gas powered boilers, and they heated those raceways, or those big tanks inside the greenhouses. And so the water is pumped. There's water that's actually pumped out to those boilers. They add heat to the water. They add that energy to the water through a fire, burning natural gas, and then that water is pumped back into the building to heat the environment for the animals. Indoor systems with aquaculture, you're going to have the greatest control over temperature, obviously. This is just an example of a building that we insulated recently to give better control of temperature. And obviously an insulated building is going to be better than a greenhouse in terms of retaining that energy, retaining that heat. We normally heat the air and the water. This is an important consideration, especially when you have a lot of tanks in a room. If you don't heat the air and you do heat the water, you get a lot of condensation on surfaces and a lot of moisture in the air. Whereas if you can heat the air as well as the water, especially if you're growing warm water animals, then you reduce the moisture content in the air quite a bit. And keeping the air circulated in the building is also very important. Dissolved oxygen is probably the most urgently critical parameter that we measure in aquaculture. This is the one that in most systems, it depends on the system, but in most systems, especially the more intensive systems where we have more animals in a smaller space, oxygen tends to be the most critical parameter. It's usually the highest cause of mortality in aquaculture. It's also very important in nature, of course. If you hear about dead zones, like the one in the Gulf of Mexico, for instance, one of the big problems there is that there's depletion of oxygen, and especially a lot of the animals that can't get out of the way of that very quickly are negatively impacted by that. The solubility of oxygen, though, in water depends on the temperature, elevation or pressure, and salinity of the water. The higher the temperature, the less oxygen can dissolve into it. Same with elevation. It's a lower pressure at higher elevations, and so less oxygen can be dissolved into the water at higher elevations. Lower atmospheric pressure, that is. And also at higher salinities, less dissolved oxygen will be found in water typically. And so safe levels of dissolved oxygen generally are going to be greater than 5 milligrams per liter, and there's a variety of different instruments you can buy to measure dissolved oxygen. Most of the instant read instruments are going to be, the ones that you can actually just stick in the water, are going to be rather expensive, around at least the $200, $250 range or higher. Some of the nicer ones are considerably higher than that. If you can get a optical probe, that's the best probably. It's one of the newer technologies though, so it tends to be a little more expensive than some of the other probes, such as galvanic and polarographic probes. Those are going to be the cheaper ones. So what we do to keep oxygen high in the water, we use aerators a lot of times. These are a couple of common aerator types for pond aquaculture systems. Aerators increase the diffusion rate from the atmosphere into the water. So basically what they're doing is splashing the water around and making more contact between the atmosphere and the water. There's going to be more surface area of the water exposed to atmosphere by breaking it up into tiny droplets or sheets of water rather than just a flat surface like what you would find in the pond otherwise. And you're also breaking and mixing that saturated surface layer. If in a still body of water, the surface layer has the highest amount of oxygen typically, because that's where the oxygen from the atmosphere goes in first, and so you're breaking that up and mixing it into some of those deeper layers, which usually have less oxygen. Then we have blowers. These machines actually, just as their name implies, blow air into the water. They're usually pretty low pressure, but they can move, in many cases, high volumes of air and pump it into the water. And then we put this through diffusers, which the diffusers, again, they break that air up into small pieces, or bubbles in this case. And these small bubbles, again, increase the amount of contact that the water has with the atmosphere. All you're doing is blowing atmospheric air into the water, but in order to really maximize the efficiency of that, you need to put it through something else. Some of these are made out of like a pumice stone type material that breaks the air up into bubbles. Others are made up of different rubber materials and things like that. And then the next step to really get a lot of dissolved oxygen or a lot of oxygen into the water is to use pure oxygen gas. Compressed oxygen gas travels pretty well. You can buy it in cylinders. A lot of times when we're moving fish or shrimp, we use this on the back of the truck because you can just put the tank on the back of the truck, open it up, and pump oxygen or supply oxygen directly into the tank. Obviously, you can get a lot more oxygen in than if you were just pumping air into the tank. It can be rather expensive. You don't want to, most aquaculture operations don't use pure oxygen on a regular basis, more on an emergency basis or on, like I said, on transport. The next parameter we come to, that's very important, is pH. And pH it's kind of a mind-boggler. It's actually the negative log, the inverse log of the hydrogen ion concentration. So it's actually, so the higher the pH, the less hydrogen ions, free hydrogen ions you actually have in the solution. And so it's inverse. It's kind of tricky to think about it that way. But what's important really is that 7 is neutral, pH of 7 is neutral. Greater than that, we say that the solution is basic, and less than that, we say it's acidic. It's more of an acid. And also what's really important is that each pH unit is actually a multiple of 10. It's a logarithmic scale, so it's a multiple of 10. So going from a pH of 7 to a pH of 8 is not just one unit. It's a very substantial change in terms of pH. Marine systems are about a pH of 8. In Kentucky, in this region, in Frankfort, Kentucky, the water, tap water, generally, unless they've treated it some other way, generally straight out of the tap or out of the river is about 8 to 8.2 or so pH. It's rather basic. And that's part of the reason for, actually it's a really good quality for aquaculture. In most of our systems, the pH tends to go down. And so starting at a higher pH is a good thing. It's also good for the bourbon industry. It's one of the reasons why the bourbon is a really popular industry in this area. And so there's this relationship between dissolved oxygen, pH, and carbon dioxide. And so what happens typically in a pond is that a pond with an appreciable amount of algae, which is most of your lower stocking density ponds. During the day, dissolved oxygen goes up because the algae produce oxygen. And they actually consume carbon dioxide. Carbon dioxide drives down pH, so taking that away allows the pH to also go up with the dissolved oxygen. And I won't get into the details, but carbon dioxide forms carbonic acid in the water and drives down pH. So during the day, DO and pH go up because of all the algae that are producing oxygen. They're doing photosynthesis. At night, the CO2 then goes up because what happens is those algae switch. They're performing photosynthesis during the day, and then when the light's gone, they don't do that anymore. They actually perform what's called respiration, along with the fish are respiring, which means they're breathing. And so there's a lot more of that respiration, which actually consumes oxygen, takes more oxygen out of the system, and puts more CO2 in. So anyway, that's why we get these fluctuations. And this isn't a perfect graph, but more DO, higher pH during the day, lower carbon dioxide, and then the inverse is true at night. More CO2, lower DO and pH at night. Okay, so that's a little bit about temperature, dissolved oxygen, pH. Now, another really important thing is the nitrogen cycle. And most of the nitrogen that comes into our water, most of it, in aquaculture at least, it comes from the feed. And the ultimate source of that is primarily the protein that's in the feed. A lot of animals, largemouth bass for instance, Carnivorous animals especially require higher protein levels in their diet. The shrimp that I work with, for instance, require about 35% protein in their diet. And so that actually breaks down through catabolism, decomposition, excretion. They break down the amino acids, they break down the proteins, and what comes out is ammonia. And ammonia is very toxic to the animals. We have to do something about the ammonia. When ammonia comes out and it's dissolved into the water, there's an equilibrium that's formed between ammonia and ammonium. NH3 is the unionized form, that's ammonia. NH4 is ionized, it has a positive charge, and that's ammonium. And ammonium is safe to aquatic animals. Ammonia, the unionized one, is toxic, very toxic. And then there's a few factors. I told you there was a lot of interactive effects of these water quality parameters. I didn't lie to you. There are. So if you have to watch this presentation a couple times, I don't blame you, because it gets rather complex, especially when we're talking about the interactive effects. But pH, higher pH favors that unionized ammonia. Higher temperature favors that unionized ammonia. The higher salinity actually favors the ionized ammonium compound. And so higher salinity can afford you some protection from toxic ammonia. Now, when that ammonia gets out into the water, there's a few different ways it can go. Ammonia or ammonium, they're interchangeable at this point. They go back and forth depending on the pH and temperature, possibly the salinity. So, one place that the ammonia can go, or the ammonium, is into algae. And algae and other plants, aquatic plants, take up ammonia directly. They assimilate the ammonia and they use the ammonia, they use the nitrogen in the ammonia to build proteins themselves. And algae use solar energy, as I mentioned previously. They use the energy from the sun as an energy source. They use CO2 from the water as a carbon source. So they actually take up CO2, they produce oxygen, and they take up ammonia as well. Heterotrophic uptake, and we're actually heterotrophic organisms. Heterotrophic organisms such as heterotrophic bacteria in the water and in the soils of the pond, or in some of our more intensive systems, we have bacteria that are on what we call biomedia, which can be plastic biomedia, or it could even be natural solid particulates that are in the water with the animals. These heterotrophic bacteria and aquatic fungi, things of that nature, also take up ammonia directly. They form cellular proteins out of it. They use carbohydrates as an energy source, just like we do and other mammals and other heterotrophic organisms. And they consume a lot of oxygen, though, and they generate CO2. They also consume bicarbonate or alkalinity. Then there's another process that we rely on. This is especially common in intensive aquaculture systems where we have a lot of animals in a small area, but this occurs in soils of ponds, it occurs in the sediments, in estuaries and oceans and rivers and everywhere else. And that's the process of what we call nitrification. And nitrification is a two-step process. First, ammonia is converted to nitrite, and then nitrite is converted to nitrate. Nitrite is NO2, and nitrate is NO3. And so what happens is that there's two groups of microbes, bacteria, and actually fungi can do this too. But these two groups of microbes perform that two-step process. And it's an oxidative process. They actually oxidize the ammonia and then they oxidize the nitrite. O2, oxygen, is required. This also consumes carbonate ions, which in turn leads to a drop in the pH. And these organisms also produce CO2. The important thing here is that ammonia is very toxic, and then nitrite is much less toxic. So unionized ammonia, you never want to see that, typically above about 1 milligram per liter. Even that is really high for some animals. Nitrite, probably, it depends largely on the species, but many animals are going to be tolerant of that up to about 5, maybe even 10 parts per million. Whereas nitrate, it's almost an order of magnitude higher, up around 100 to 200 parts per million is where we see some toxic effects of nitrate. And so that's why it's nice in many cases to encourage this process of nitrification, because if we can get all the nitrogen over to nitrate, it's much less toxic to the animals. So how do you deal with these things? How do you deal with ammonia if you're not relying on some of those algal and microbial processes? Well, for better or for worse, a lot of aquaculture operations dilute. They pump water through a facility. There's cage culture as well, where animals are actually out in the environment. They're stocked hopefully very carefully in a way that the waste product, the ammonia, is assimilated into the environment and it doesn't cause any environmental harm. Same way here with a lot of aquaculture operations. This is a pumping station at a large shrimp farm. I believe this one is in Ecuador. And water is pumped through these ponds to dilute the ammonia. And that's another very common solution to ammonia and some of the other compounds that build up in our aquaculture systems. Trout raceways, for instance, often use groundwater that comes into the raceway and then it's flushed out of the end of the raceway, and that dilutes largely the ammonia, brings in water that's higher in oxygen as well. Then oftentimes when in water treatment we look at two things. We look at the nutrients, the dissolved components, and we look at the solids. And the treatment processes for those are usually separated. They're usually at least thought of as separate processes. So what are solids made of? Solids can be just detritus, can be fish scales or exoskeletons from crustaceans, pieces of those that are broken down in the water. A lot of the solids are, it could be feces, uneaten feed, sediment that's in the water, clay particulates, all kinds of things. And many of these solids have microbes, algae, and other small critters living on or within them, including zooplankton and things of that nature. Microbes especially excrete exopolymeric substances like bacteria. They create things that are normally called a biofilm. In this case, when they do that out in the water, a lot of times they form these particulates in the water. And in nature, that's called marine snow. In some of our more intensive systems, we call it biofloc because these microbes have flocculated together and they're full of biota, or living organisms. Why do they do that? Well, there's ecological reasons for it. There's safety in numbers. There's near that organic food source that they all mostly need. And so we get these particulates that develop naturally in the water from microbes a lot of times, which is actually a really interesting field of study as well. What contributes to the level of biosolids? The more you feed your aquaculture system, the more solids are going to be produced. Sometimes the more turbulent the system is, the more you kick up sediments, things like that. Some species such as koi, for instance, really stir up the bottom of ponds quite a bit, and they'll tend to have more solids suspended in the water. The density of the animals has a lot to do with it. Density also affects feed rate. Inefficiencies in feed conversion. No animal is perfectly efficient or even close to it in terms of all the feed going into their tissues. So some of it's excreted, ends up as solids in the pond or the system. And the different types of microbes and the microbial biomass that accumulates as a result of that, and the different organisms that live in the water with the animals. A lot of times, water quality is not just the water, and it's not just the nutrients that are in the water, and it's not just the fish or the shrimp. It's actually, there's a lot going on in a body of water oftentimes, including bacteria and algae and zooplankton and the like. And you have to be aware of those things that are going on as well and what implications they have for your animals. So why do you want to control solids? Well, too many solids in the water can lead to gill clogging. It leads to an increased demand of oxygen because most of those microbes also consume oxygen. So they're going to bring down your dissolved oxygen, which again is the most critical factor in water quality in aquaculture. They promote the occurrence of harmful microorganisms such as cyanobacteria love high solids environments, which in this picture that's mostly cyanobacteria. And there's potential for these solids to accumulate on the bottom of ponds and tanks, which we just call sludge. And as its name implies, sludge is not very nice to have around. It can create anaerobic areas, which are dangerous for the animals. You want to have control over the system, then you control the amount of solids that are in the system. A lot of solids means a lot of organisms, and so having that in the water can make the system a little bit less stable. And we're also taking out nutrients and encouraging proper nutrient cycling by doing that. So how do we remove solids? Well, there's a variety of different filtration techniques. A lot of times in ponds you can design the pond where your solids might accumulate in one section and they can be removed. Some large ponds even have a slope towards the center where there's a drain and solids can be removed from that central drain. A lot of tanks are designed that way as well. In the more intensive systems we have filters like the ones that you see here as well. Bead filters, water passes through a bed of beads and the solids are stripped out by those beads, and then what typically happens is once those beads are clogged with solid particulates, you turn off the water to the filter and you pump water in the opposite way, which dislodges a lot of the solids and causes them to fall down to the bottom of the filter. You open a valve and purge that off, and that's your called backwash from the filter. We've got other things too. Foam fractionators are really neat. They're used a lot of times in home aquariums. They're used a lot in public aquariums too. If you ever get the chance to go backstage behind, especially the saltwater exhibits at your local public aquarium, you will most likely see foam fractionators. You inject a lot of air into a chamber, which makes a lot of foam. And basically what happens is all the little bubbles that are moving up through the water column attract the solid particulates, and that foam that comes out of the top is real dark brown. If you've ever seen sea foam on the beach, sometimes it's not real attractive, sometimes it's kind of dark brownish color. It's the same concept. The foam actually attracts the solids and pours out of the top of these fractionators, and then we collect that and dispose of it properly. And there's a variety of other filters, including sock filters, which, as their name implies, basically like passing water through a sock, or particulate filters, like kind of like your coffee filters at home, basically, that trap certain sizes of solids. And it depends on what size solids you want to remove and how much of them you really want to remove. If you want crystal clear water, then you need to have a really robust solids filtration system, especially in the more intensive systems. If you don't need crystal clear water, then you can back that down a little bit. And importantly, the level of solids and the level of all these water quality parameters really depends a lot on your application. If you're working at a drinking water facility and you want to have drinking water for a municipality, then you need to have really clean water with no solids, very, very low nutrient content like ammonia, and you need to disinfect the water as well. Disinfection is a whole additional ball of wax, I guess, but it can involve things like chlorine or ozone, and ultraviolet light can actually kill a lot of the microbes in the water. But if you're raising catfish in a pond, then that's kind of the other extreme, where catfish can tolerate a wide range of water quality parameters, and so you don't need to have that level of control over the system. You can allow some solids to accumulate and allow some nutrients to accumulate as well. So it all boils down to what your specific goals are and how you tailor your water management techniques to meet those goals. This is the book that we use in my water quality management class in the Division of Aquaculture. It's a good handbook to have around. It's rather inexpensive as well. And with that, I thank you very much for your time. Let me know if I can answer any additional questions.